Welcome back to The Explainer. Today, we're going to run a sort of diagnostic check on the universe itself. We're diving deep into the absolute ultimate rules that govern energy, work, and literally the flow of time. So, let's just jump right in, shall we?
All right, let's start things off with a question that, honestly, might sound a little silly at first, but it's actually profoundly deep. Why can't a popcorn kernel unpop? I mean, think about it. If you saw a video of an exploded piece of popcorn suddenly shrinking and perfectly reforming into a smooth little kernel, you'd know instantly, hey, that video is playing in reverse, right? This right here is our everyday macroscopic experience of a one-way, irreversible process. But what's the actual underlying physics that absolutely prevents it from going backward? Well, that's exactly what we're going to decode today.
So here's our system diagnostic check for today. We're looking at the arrow of time, the second law, the ideal heat engine, refrigerators and real engines, and finally, entropy from a statistical view.
Module 1. The arrow of time and our macroscopic reality.
Okay, so the key to understanding why our popcorn won't unpop involves this fascinating property called entropy, usually symbolized by the letter S. Now, what's really interesting here is that entropy is what we call a state property. That basically means the entropy of a system depends only on its current state. It doesn't care at all about the path it took to get there. But here's the absolutely crucial distinction. Entropy is not like energy. You know energy is always conserved, right? It never changes in a closed system. Entropy, on the other hand, it doesn't obey a conservation law at all. For irreversible processes, the entropy of a closed system always increases. And that, my friends, is exactly why it's so often called the arrow of time.
So how do we actually measure this stuff? Well, the change in entropy, delta S, is defined by the integral of dq over T. In this equation, dq is the energy transferred as heat to or from the system during a process, and T is the temperature of the system in kelvins. And here's a neat little trick. Because temperature in kelvins is quite literally always positive, the sign of the entropy change is perfectly locked to the sign of that heat transfer. Makes sense, right?
Let's look at a classic example to see how this builds. Imagine the free expansion of an ideal gas. Picture this. We start with a gas totally confined to the left half of a thermally insulated container. Then, boom, you open a stopcock, and the gas instantly rushes out to fill the entire container. This is your perfect visual example of an irreversible process. I mean, those gas molecules are never going to spontaneously organize themselves and rush back into just the left half, right? No way. Now, fun fact, to actually calculate the entropy change here, physicists have to imagine a reversible, super slow isothermal expansion that reaches that exact same final state. Why? Because as we just said, entropy is a state function.
Which brings us to our second module, Section 2, the second law, the absolute ultimate rule. I want to read this quote to you directly because this is literally the fundamental law governing our reality. Ready? If a process occurs in a closed system, the entropy of the system increases for irreversible processes and remains constant for reversible processes. It never decreases. Now, okay, it is true that you can decrease the entropy in just a part of a system, like say freezing water into a nice highly ordered ice cube, but you absolutely must include the surrounding environment in your calculation. When you look at the whole entire closed system, the net entropy always goes up, period.
And that brings us to this brilliantly simple inequality. Delta S is greater than or equal to 0. It tells you exactly which way time flows and which processes are actually possible in our universe. It's that simple and that profound.
Let's shift gears from theoretical physics over to mechanical applications. Section 3, the ideal heat engine and harnessing heat.
So, what is a heat engine? It's simply a device that extracts energy from its environment as heat and does useful work with it. It needs a working substance, like steam or maybe a gas-air mixture, that operates in a continuous cycle. Well, way back in 1824, this brilliant engineer named Sadi Carnot figured out the absolute ideal reversible limit of such an engine. It's called a Carnot cycle, and it consists of 4 strokes. First, an isothermal expansion, where it absorbs heat at a high temperature. Second, an adiabatic expansion, where it does work while dropping in temperature. Third, an isothermal compression, where it loses waste heat at a low temperature. And finally, an adiabatic compression that returns the whole thing right back to its starting state.
Now, you know inventors. They're always trying to beat this cycle. The ultimate inventor's dream is this mythical, perfect engine that converts literally 100% of the heat it absorbs directly into work, with absolutely zero waste. Imagine a giant ship powering itself just by sucking heat out of the ocean water.
Sounds amazing, right? But thermodynamic reality is pretty harsh. A Carnot engine proves that while you extract heat and do work, you absolutely must discharge the remaining heat to a low-temperature reservoir. A totally perfect engine? It's literally impossible, because it would outright violate the second law.
We actually measure an engine's success by its thermal efficiency. And for the ideal Carnot engine, the efficiency is simply 1 minus the ratio of the low-temperature reservoir over the high-temperature reservoir. Just look at that math for a second. The only way you're going to get an efficiency of 1, meaning 100%, is if your low-temperature exhaust is sitting at absolute 0. And yeah, that is practically impossible. Let's ground all this math in some reality. Take the North Anna nuclear power plant in Virginia, for example. It is this massive, incredibly complex heat engine. It generates 900 megawatts of useful electric power. Awesome, right? But bowing to the Carnot limit, it is literally forced to discard 2,100 megawatts of heat into a nearby river. Just really think about that for a second. Even our most advanced, state-of-the-art power plants throw away way more energy than they actually deliver. And it's all because of the uncompromising rules of entropy.
So what happens if we take these cycles and run them backward? That's section 4, refrigerators and real engines.
Basically, a refrigerator is just a heat engine operating in reverse. It's a device that uses work, usually from an electrical compressor, to transfer energy from a low-temperature reservoir, like the inside of your food compartment, over to a high-temperature reservoir, like your warm kitchen. Now, we don't actually measure a fridge by efficiency. Instead, we use something called the coefficient of performance. It's basically a ratio. It's what we want, which is the cooling, divided by what we pay for, which is the work required to pump that heat against the natural gradient. So the really crucial point here is that even a Carnot refrigerator, the absolute ideal setup, still strictly requires an input of work to move that heat around. Another classic inventor's dream is the perfect refrigerator. That's one that just naturally moves heat from a cold place to a hot place with zero work input. Like, imagine an unplugged fridge that just sits there and cools itself. Obviously, totally impossible. But why? Because without that external work input, the net entropy of the entire system would actually decrease. And that completely violates the second law of thermodynamics. Long story short, you can't beat the heat without paying for it with work.
And this leads us to wonder, why do our actual cars and fridges fall so ridiculously short of even the ideal Carnot limit? Well, because the real world is just messy. Real systems have irreversible processes everywhere. You've got friction rubbing mechanical parts together, you've got turbulence in the gas, you've got wasteful heat leaks left and right. So while a Carnot car engine might theoretically hit something like 55% efficiency, your actual car engine? Yeah, it's hovering somewhere around 25%.
Okay, let's zoom all the way down now, from massive power plants right down to the microscopic realm. Section 5, Entropy, a statistical view.
You know, it's crazy to think the laws of thermodynamics were discovered by guys studying bulky steam engines, but they are actually driven by the tiny statistics of molecules. Imagine a box with just 6 gas molecules bouncing around inside. We can group their arrangements into configurations. Take a look at configuration I on this table. All 6 molecules are in the left half. There's literally only one way, or one microstate, for that to happen. Its multiplicity, labeled W, is just 1. But now look at configuration IV. 3 molecules on the left, 3 on the right. There are actually 20 different ways to achieve that specific arrangement. Statistical mechanics essentially views entropy as a giant game of probability. The most evenly distributed microstates simply have the highest multiplicity. To bridge this microscopic game of chance with our macroscopic reality of temperature and heat, we need a very special key. Enter the Boltzmann constant, 1.38 times 10 to the negative 23 joules per Kelvin. In 1877, the physicist Ludwig Boltzmann used that exact constant to derive his absolute masterpiece, his famous entropy equation, S equals K times the natural log of W. Put simply, entropy is the Boltzmann constant multiplied by the natural log of a state's multiplicity. This formula is so profoundly fundamental to the very nature of reality that it is literally engraved on Boltzmann's tombstone. The logarithm perfectly connects the multiplicative nature of statistical probability with the additive nature of macroscopic entropy.
So let's tie this whole thing together. Why does heat only flow from hot to cold? Why does our gas fill the whole container? And going back to our very first question, why doesn't that popcorn kernel unpop? It is not because there are physical laws actively acting like bouncers, preventing atoms from moving in a reverse path. It is simply because those unpopped or separated configurations have a macroscopic multiplicity that is statistically unfathomably improbable.
High entropy just means maximum multiplicity. The universe moves forward simply because it's constantly moving toward the most probable state. Which leaves us with one final, kind of mind-bending thought to wrap up our system diagnostic today. We know for a fact that entropy always increases in a closed system. So, if we consider the entire universe to be one giant closed system, what exactly happens to time, to energy, and to work when its multiplicity finally reaches the absolute maximum and there's literally no more probability left to explore? Think about that for a while, and as always, keep learning.